Applications of integration, last page. We're just going to continue doing some more rotations, or they call them revolutions, I guess. The shaded region is rotated through 360 degrees about the x-axis. Find the volume of the revolution. Okay, so the shaded region. So it looked kind of like that, right? We would be integrating from 5 to 8, because those are the x-axis limits. The function is x squared plus y squared. Ooh, so we need to put this in terms of y equals something. So we would have y squared equals 64 minus x squared. And that would be y equals square root of 64 minus x squared. So we would be integrating from 5 to 8, and first we would put pi, and then inside we would put 64 minus x squared dx. Yeah. Oh, but we would square the r. That would actually make it simpler, wouldn't it? It would be pi times 64 minus x squared with no root dx. Yeah, that's a much easier integral. So we would integrate that, and we would get pi 64x minus pi x cubed over 3. And then we would put the limits of integration as 5 to 8. And while you admire that, I am going to make it a little bit smaller. Okay. So now I substitute in the 8. Get pi times 64 times 8. What the heck is 64 times 8? I know it's a famous number. 512. Minus pi x cubed, 8 cubed. 8 cubed. 8 times 8 is 64. Times 8 is, it's also 512. So it's going to be minus pi 512 divided by 3. And then I subtract the same expression with 5 substituted in. 64 times 5 is 320. So it would be pi 320 minus 5 cubed, which is 125. Pi 125 divided by 3. Okay. Now let's try to simplify this. Pi 512 minus pi 512 divided by 3 would be 2/3 pi 512, right? 2/3 times 512 times pi minus 320 pi minus 125 divided by 3 pi. Actually, it's not minus 125 divided by 3 pi. It's a minus, so that would be plus, right? I almost did that wrong. So I did do it wrong. I'm just going back and fixing it now. So 1,000, I could combine this one and this one because they're both over 3. Maybe it's going to come out nice and round. So 1,024 plus 125, 1149. Is that divided by 3? Is that divisible by 3? Yeah, it is. So then we divide by 3, we get 383 pi when we combine those purple ones. And we subtract 320 pi, and that gives us 63 pi. 63 pi. Okay. Let's shrink this down a little bit. And then we can do the next part. All right. So that was find the volume of revolution. A hemispherical bowl of radius 8 centimeters contains water to a depth of 3 centimeters. What is the volume of water? Actually, they're describing this very bowl, right? Hemispherical bowl of radius 8. That doesn't mean that this bowl is 8 centimeters radius across the top. It means that it's made out of a sphere that has a 8 centimeter radius like this one. So, and the depth of 3 centimeters, we're talking about this depth of 3 centimeters. 8 minus 5 is 3. See, so they're actually talking about this bowl. So actually all they're saying is, hey, what did you get for part A? And at 63 pi, if you want to put it in a decimal or something to make it a number that sounds more like a volume, you could say 63 times 3.14 equals 198. 198 centimeters cubed. Yeah. Okay. Number 7. A circle with center 0, 0 and radius r units has the equation x squared plus y squared equals r squared. If the shaded region is revolved about the x-axis, what solid is formed? Okay, and use integration to show that the volume of the revolution is 4/3 pi r cubed, which may be recognized as the volume of a sphere. So yeah, if you take this shaded region and you rotate it, you should get a sphere, right? So let's actually use the integral to calculate the area of the sphere, or the volume of the sphere, which is 4/3 pi r cubed. So first of all, let's take this equation here and change it into a function in the format y equals blah, blah, blah. First we do y squared equals r squared minus x squared. Then we do y equals the square root of r squared minus x squared. And then we put that into our integral. We're going to integrate from negative r to r. We're going to put pi, and then the r here is going to be the function, which is square root of r squared minus x squared. We're going to square that so we can get rid of the radical too. Oh, wait a second, the r. Oh yeah, we just leave r. R is a constant. And then the height of the flat cylinder is dx. So that's not a bad integral to do. If we're going to integrate pi r squared, we're going to get pi r squared x. Remember, r is not a variable. It's just a constant. So we just leave it there. And then we introduce the variable x. Now, pi x squared, x is a constant. X is a variable. So then we're going to do minus pi x cubed over 3. And then we're going to evaluate it from negative r to r. So we're going to plug in r in for x here, and we're going to get pi r cubed minus pi r cubed divided by 3. And then we're going to subtract this expression, evaluate at negative r. So it's going to be negative pi r cubed, and then minus pi, and then negative r cubed is going to be plus pi r cubed divided by 3. So pi r cubed minus pi r cubed divided by 3 is 2/3 pi r cubed. And then this one is going to be pi r cubed divided by 3 plus... Well, let's do these separately. So minus a negative pi r cubed is going to be plus pi r cubed. And then we have minus 1/3 pi r cubed. Okay, now what do we get? So 2/3 pi r cubed minus 1/3 pi r cubed is going to be 1/3 pi r cubed. Plus 1 pi r cubed is going to be 4/3 pi r cubed. Okay, so we did get that. So that's the answer to part B. Part A, they're saying what solid is formed. We already said that. It's a sphere. All right, moving on. Last one, number 9. Sketch the graph of y equals sine x plus cosine x for 0 to 2 pi over 2. So, sine x plus cosine x. Can you imagine what that might look like if you added these together? It should just be another sine wave. Did you know that if you add sine and cosines together that they just make more other sine waves out of phase? So like this one would be start at 1, and then at the midpoint it would be -1, and like here it would be like higher, and where would be the maximum? Maybe like here. Here would be 1 at the end too. It would look kind of like this. It would be a sine wave also, but just shift it a little bit. Okay. And then do it for 0 to pi over 2, which would be like about here. So the region you're going to rotate is about like that. Okay. You're going to hence find the volume of revolution of the shape bounded by that, the x-axis, 0, and pi over 4. Oh, pi over 4. So actually you're going to have like half of that. Okay, when it is rotated about 2 pi. Do you want to, let's draw on the calculator. Their picture is going to be much better than mine anyway. So we're going to put sine x plus cosine x. Sine x plus cosine x. We're going to graph it. And see, it's just a sine wave. Just like, it doesn't start exactly at 0 though. We're interested in the part from 0 to pi over 4. What is pi over 4, by the way, in numbers? It's 0.785. So I am going to, just to make it easier for us, I'm going to show you what it looks like from 0 to 0.785. And then we can change the y-min to like -2, -2, and the y-max also to like +2, and then we'll graph again. Okay. So it's just part of the, it's just part of it now. So this part that appears on the calculator kind of looks like that. It's actually like, let's rewrite this in a different color. It's actually this part right there. And so we could draw these vertical lines here and the horizontal line here. And this is a cross-section of the thing we're going to rotate. So we're going to rotate this now, and we're going to make a little cup or bowl or something on its side. It's going to be kind of like that. Okay, so what does the integral look like? The integral is going to go from 0 to pi over 4, because that's what we said. 0 to pi over 4. And the function, oh, remember that we need to put the equation for the little cylinders we're going to cut it up into. It's going to be pi times the r, which is the function itself, squared dx, which is the height of the flat spheres. Okay, and then we can multiply that out because we can't take the integral of something kind of complicated like this. So we're going to multiply it out, and we're going to have pi times sine squared x plus 2 sine x cosine x plus cosine squared x. Okay, and that is the same. We're about to take the integral. We haven't taken it yet. Now notice that we have sine squared plus cosine squared, and we know that sine squared plus cosine squared is an identity. It's equal to 1. So actually we can simplify this. Even before we take the integral, we already know it's 1 plus 2 sine x cosine x dx. And now we can also, like, we can't take the integral of sine times cosine, but we do know that 2 sine cosine is also an identity. It's sine 2x. So we can rewrite this again. We could write it as 1 plus sine 2x dx. So now we can take the integral of that. So the integral of 1 is x. The integral of sine 2x is something like negative cosine 2x, maybe divided by 2 because of the chain rule. Let's test that out. Take the derivative of cosine is negative sine 2x, and then the chain rule gives you an additional 2. Oh, and then I had the 2 from the bottom here. I had the original negative. The negatives cancel out. The 2's cancel out, and I get sine of 2x. And that's what I have here. Oh, okay, so it worked. Okay? So, we guessed that it was this, and we took the derivative, and we guessed correctly. So now we can evaluate the integral from 0 to pi over 4 finally. So we first put pi over 4 in there, and we'll get pi over 4 minus cosine of 2 times pi over 4, which is pi over 2. The cosine of pi over 2 is the cosine of 90 degrees. Cosine of 90 degrees is 0. So, 0. Then we subtract that expression with 0 in it. So that would be 0 minus cosine of 2 times 0, which is cosine of 0. Cosine of 0 is positive 1. Divided by 2 is 1/2. So now we have pi over 4 minus 1/2, which is plus 1/2. And I think that's it. Yeah. Okay. Yep, that's it.